Today we're going to continue talking about matchings, and we're going to talk about some other related parameters as well. So let me just remind you of what we've seen so far. So we had the definition of a matching, and basically a matching was a set M of edges such that no two edges in M share an endpoint. So if I have a bunch of edges and they're completely separate from each other, if I have something like this is a matching. And I can have other edges in my graph as well. But the blue part is a matching. And then we talked about the difference between maximum and maximal matchings. The idea was that we say a matching is maximal if we cannot add any more edges to it. If adding any other edge would make it no longer a matching. And we said it's a maximum matching if it has the largest possible size among all matchings. Now, we also had this concept of an augmenting path. So given a graph G and a matching M, an augmenting path is a path that alternates between edges of M and edges outside of M, but it starts with an edge that is outside of M and also ends with an edge that is outside of M, right? So if, let's say, I show my matching edges in blue, an augmenting path would be something like this. It would be a black edge, so an edge that is not in my matching, followed by a blue edge, followed by another black edge, and so on. It alternates in the color, and it starts and ends with a black, right? And if I have just one black edge on its own, that's also an augmenting path, right? So what can I do with an augmenting path? Anyone? So I can extend the size of my matching, right? So, and also the idea here is that this vertex should be unmatched. And I'm talking about an augmenting path, and this vertex should also be unmatched. And if both of these vertices are unmatched, I can just take this augmenting path and I can basically switch. I can put all the edges that were not in the matching into the matching. So I can just change the color of every edge here. I can say every black edge becomes blue and every blue edge becomes black. And that will give me a bigger matching. And then we saw this theorem last time. Which basically said a matching M is maximal. Sorry, it's maximum if and only if it has no augmenting paths. So if I cannot extend a matching, then it's a maximal matching. So I cannot extend the matching using augmenting paths. Now, one side of this theorem was trivial, because if I do have an augmenting path, I can make my matching bigger. So of course, my matching is not maximum, but we also proved the other side. And the way we proved the other side was that we said, okay, let's say this matching M is there. Let's take a maximum matching M star. Let's look at their difference. Let's look at their symmetric difference, the delta. And then we use that to find an augmenting path. Okay. But now I want to look at a different thing. I want to say, suppose my graph is bipartite. What can I say about a maximum matching in a bipartite graph? So suppose G is a bipartite graph. And let's say it has two parts, with parts X and Y. Okay. And let's say that X is the smaller part. So let's say the size of X is less than or equal to the size of Y. I want to see if it's possible to have a matching that basically covers every vertex in X, that matches every vertex in X. So here's an example. Let's say I have my set X here. Remember, I want X to be the smaller set, or if they are equal, it doesn't really matter. And then I have Y here. And I have some edges. The question is, do I have a matching? Of course. Do I have a matching that covers all of X? Well, in this case, yes. Right. So just take this very trivial matching here, covers all. But I want to find a condition that is both necessary and sufficient for having a matching that basically matches all of X. I don't care if all of Y is matched because Y might be bigger than X and I have a bipartite graph, so maybe it's even impossible to match everything in Y. But I want to see if I can match everything in X. Okay. So first of all, suppose that I do have such a matching. Suppose that I have a matching that has matched everything in X to something in Y. Right? If I look at any subset of the vertices of X, so let's say consider any subset, let's call it S subset of X. And if I look at all the neighbors of S, so I write that as N of S, and N of S is basically the set of all the vertices in Y that have an edge to any of the vertices in S. Right? So S is not a single vertex. S is a set of vertices, but I can still talk about the neighbors of these vertices. It's just the union of the neighbors of each of them. Right. So what happens if I look at the neighbors of any subset S? So for example, let's say these two vertices are S, and I look at their neighbors. Now, if I have a matching, it means that at the very least, the set of neighbors is going to contain the vertices that were matched to the vertices in S. Right? And so here I have two vertices in S. Each of them were matched to something in Y. So together, these two vertices should have at least two neighbors. Of course, in this case, they have much more than two neighbors, right? But in general, what I see is that the size of neighbors of S should be greater than or equal to the size of S. Because every vertex in S is matched to one of the vertices in the neighbors of S. And it's impossible to match two of them to the same vertex because that's against the definition of a matching. They cannot share. So this is a very trivial result. Whenever I have a matching, if I take a set S, which is a subset of X in this case, the neighbors of S are more than or equal to S. But what's interesting is that this is also sufficient. So this is Hall's theorem. So this is the theorem by Hall. Basically, it says in a bipartite graph, XY bipartite graph, we have a matching that covers all of X, there is a matching M. I think they don't call it cover. I don't know why, but they constantly use different words. They say saturate or something. So there is a matching M saturating X if and only if for every subset S of X, the number of neighbors of S is at least as much as the number of elements. S. So we've already seen one side of this. So if I have a matching, then for every subset S of X, the number of neighbors of S should be greater than or equal to the size of S. This is the trivial thing here. The interesting part is that the opposite also holds. So the interesting direction, the non-trivial direction is this direction that I'm going to prove. So suppose that every subset of X has enough neighbors. Then I want to say that there is a matching that saturates all of X, that matches everything in X. Okay. If you were to choose a matching, which matching would you choose here? It makes sense to just look at the maximum matching, right? Because we're talking about a bipartite graph. So the size of my maximum matching is going to be at most the size of X. My matching cannot have more edges than the number of vertices in X. So if I'm saying that I want to find a matching that covers all of X, I want to find the maximum matching, right? That's my intuition. So, but of course I have to prove that it covers all of X. So this is what I want to do. I want to say, suppose this condition holds, I want to take the maximum matching, or if there are several, then I want to take one of the maximum matchings. And I want to say that it definitely covers all of X. So I say this, I say, let M be a maximum matching. Okay. And just to do proof by contradiction, suppose that it doesn't cover all of X. Okay, suppose that M does not saturate all of X. Okay, so what does this mean? Let's just draw another picture here. So I have X on one side, I have one on the Y on the other side, and then I have the vertices. And then I have some edges. And again, I'm going to draw the edges in my matching in blue. So let's say this is a matching edge, this is a matching edge, and I'm going to draw the other edges in black. Okay. Now, if my matching had already covered all of X, I would be very happy, but I'm doing the case where M does not cover all of X. So there should be a vertex somewhere here, let's call it small x, that is not matched. Okay. But if X is not matched, what can I say about it? Well, I know that if I take any subset of vertices of X, they have at least as many neighbors as the number of elements in the subset. So this X should have at least one neighbor, right? But that neighbor, that edge that is coming out of X, it's a black edge. It's not an edge in my matching. So can this vertex be unmatched? No, because if this vertex is unmatched, then I can just add this edge to my matching. Right. So if I call this one, let's say small y, this y is already matched to something else. Right. So there's going to be a blue edge coming out of y. Okay. Let me actually call this one x0, and let's call this one y0. So let's call this one x1. Okay. Now let's look at x0 and x1 together. It's a set of size 2, so it should have at least 2 neighbors. Right? So there is another edge, either from x0 or x1, that goes to some other vertex y1 here. So again, I don't care if it's x1 or x0. From one of them, I have an edge to this y1. And that edge is not in my matching because x1 was matched with y0 and x0 was not matched to anything. Now I can continue the same thing. I can say, let's look at y1. If y1 is not matched to anything, I found an augmenting path. Right. If y1 is matched to something, let's call that x2. And then let's look at x0, x1, and x2. And let's say that I have 3 vertices here, and then I should have 3 neighbors on the other side, and so on. So this is the basic idea, but let's just formalize this and let's say exactly what I'm creating here. I'm basically looking at all the alternating paths that start at x0. Okay, so I'm going to say, consider x0, which was not matched to anything. Take all alternating paths from x0. Okay. Now, if I take all the alternating paths that I can have from x0, I can reach some of the vertices on the left side in x, and I can reach some of the vertices in y. Okay. So let me just draw this again in a different way. Actually, quite hard to erase. So let's say I have my vertex x0 here. Okay. And in y, I have a bunch of vertices that could be reached from x0 by alternating paths. Let's call that something, y bar. Okay. And then in x, I'm going to also have a bunch of vertices that were reachable from x0 by an alternating path. Let's call that x bar. Okay. So y bar is again the set of all vertices in y that are reachable from x0 by an alternating path. But how do these alternating paths look like? Basically, the way it works is that x0 is not matched to anything. So the path has to start. There's a bug here. So the path has to start with an edge that is not in the matching. And then I have to take an edge that is in the matching. Then I have to take another edge that is not in the matching, and so on. Okay. But what does this mean? Whenever I add some vertex to x bar, it means that there was a vertex in y bar, and then there was an edge of the matching coming from the right to the left. So as I'm taking these paths, every time that I'm going from left to right, I'm taking an edge that is not in the matching. Every time I'm going from right to left, I'm taking an edge that is in the matching. Okay. So what does this tell you about the size of y bar and the size of x bar? So let me ask you this. When I get to a vertex in y bar, so let's say I've taken this path and I've got to this vertex. Is it possible that this vertex is not matched to anything? No, because if this vertex is not matched to anything, I've found an augmenting path, and that gives me a bigger matching. And this was a maximum matching, so I cannot have that. So I never get stuck in y bar. Whenever I get to a vertex in y bar, there is definitely an edge, and it's an edge of the matching that is going to x bar. Okay. And also, whenever I'm arriving in X bar, that's because I took an edge from a vertex in Y bar, and that was an edge of the match. So do you agree that Y bar is matched to X bar? So if you just look at the blue edges between Y bar and X bar, it's a perfect matching. It's matching every element of X bar to an element of Y bar and vice versa. Why? Because whenever, again, every element of Y bar, when I reach it, there has to be a blue edge going to some element of X bar, because otherwise I can extend my matching. And every element of X bar, by definition, was reached by going to some element of Y bar and then taking a blue edge. Right? So every element of Y bar is matched to an element of X bar and vice versa. But if I have a perfect matching between two sets, X bar and Y bar, that means that their sizes are the same. So the size of X bar is equal to the size of Y. Okay. What's the problem with this? Yes. So if I look at X bar union with X0, they need to have some other neighbor, right? So there has to be some other vertex here because the size of X bar is the same as the size of Y bar. So if I add one vertex on this side, if I add X0 here, then the neighbors of X bar and X0 should contain some other vertex here. Okay. Now, let's call this whatever, Y minus 1. So I have this Y minus 1, right? And I know that it's either a neighbor of X0 or a neighbor of one of the vertices in X bar. But is it matched to anything? No. So if I look at this, just do a casework. So let's say it's a neighbor of X0. That was the 0, not the vertex. Let's say this is a neighbor of X0. Okay. Then I can just add this edge and I will get a bigger matching. So it cannot be a neighbor of X0. So suppose that it's a neighbor of some other vertex. Let's say it's a neighbor of this X bar. Then I have this path. I have the path from X0 to that vertex plus the edge to this new vertex. And this is an augmenting path. So I cannot have that either, which means that I cannot have this vertex at all, which is a contradiction. So my maximum matching has to cover all of X. Okay. Great. So we have an easy way of checking if a bipartite graph has maximum matching, has a maximum matching that covers all of X, basically. So what I can do is I just look at every subset of vertices of X, and I count how many neighbors does this subset have. And if the number of neighbors is always greater than or equal to the size of the subset, then I say there is a matching that covers all of X. Okay. From this, we actually have a very simple corollary, which is this. I say let G be a K-regular bipartite graph. So K-regular means that the degree of every vertex is K. Okay. And suppose that K is at least 1. Okay. I want you to prove that G has a perfect matching. And a matching is perfect if it matches every vertex. So again, let's just draw a simple figure here. So I have two parts, X and Y. I have a bunch of vertices on one side and I have a bunch of vertices on the other side. And I know that the degree of all of my vertices is exactly K. So for example, let's say K is 3 here. So I have 3 edges coming out of every vertex. So the first thing is that the size of the two parts has to be equal. The size of X should be the same as the size of Y. Why is that? Because just count the number of edges. How many edges do I have in this graph? I can count them from the left side. I can say I have X vertices and each of them has K edges coming out of it. So the total number of edges is X times K. But I can also count it from the Y side. And I can say this is also equal to Y times K and then just cancel the K's. Okay, so whenever I have a K-regular bipartite graph, the size of the two parts is going to be equal. Okay. But I want to say that I have a perfect matching. I want to say that I have a matching that matches every vertex. But since the size of the two parts is equal, all I have to prove is that I have a matching that covers all of X. Because if I have a matching that basically matches every vertex of X with something, then it should also match every vertex of Y. I have the same number of vertices on both sides. Right? Okay. And for that, I know that I have to just check this condition. I have to say that whenever I take any subset of the vertices in X, the number of neighbors is enough. I have at least as many neighbors as the vertices in my subset. So let's do this. So let's say, suppose S is a subset of X. Okay. What can I say about the number of neighbors of S? So let's say I take some set S. What are the neighbors? So the neighbors are all the vertices that have any edge going from S to them. So let's do something like this. Let's say this is the set of neighbors of S. Okay. But now I want to do something similar. So in the previous step, when I wanted to say that the size of X is equal to the size of Y, I was just counting the number of edges, right? But now I say, let's just count the number of edges between these two sets, between S and neighbors of S. Okay, so what is the number of edges between S and neighbors of S? Okay, let's give this some name. Let's call it, I don't know, T. Okay, what can I say about T? Well, I can count it from the point of view of S. I can say every vertex in S has K edges going out. So T is exactly going to be the size of S times K. Right? Now I can count it from the other side, from the neighbors of S. Again, here every vertex has K edges going out, but maybe some of them go to S, some of them may not go to S. Right? So the number of edges going out of the neighbors of S is neighbors of S times K, but not all of them are going to S, right? So what I know is that this T is going to be less than or equal to the size of neighbors of S times K. Because again, remember, this is the number of edges that is going out of neighbors of S. But I'm only counting the edges that go out of neighbors of S and into S. So this is going to be less than or equal to this. Now, again, we have what we wanted, right? So S times K is less than or equal to N of S times K. So the size of S is less than or equal to the size of N of S. And that's exactly the condition that we wanted. Okay, great. So now we're going to talk about some other things. And actually, this was already in your problem set, so you will not be too surprised by this one. So we want to look at the relations between vertex covers and matchings. Okay. And again, remember that a vertex cover is a set of vertices that covers every edge, such that every edge, so I don't know, let's call it A, has at least one endpoint in A. Okay. Now, whenever we define any kind of set, so whenever we define, let's say, a matching or a vertex cover or so on, we're usually interested in knowing how big can it get and how small can it get. So what is the size of the maximum vertex cover or the minimum vertex cover and so on. And usually one of the two is kind of trivial. So if you think about matching, it's hard to have big matchings. If I give you a graph, it's kind of hard to find a big matching. But if you want to find a small matching, just take any edge, right? So when I talk about vertex cover, it's kind of the opposite, right? So it's very easy to find a large vertex cover. Just take all of the vertices. If you take all the vertices in the graph, they're definitely going to cover all the edges. That's a really huge vertex cover. But of course, what's interesting to us is what is the size of the smallest vertex cover. Okay, and in order to talk about this, I'm going to first try to find a relationship between matchings and vertex covers. So let's say I have a matching M. So suppose M is a matching. And let's say A is a vertex cover. Remember that this one is a set of edges, but this one is a set of vertices. Okay. But what can I say about the relative size? Which one is going to be bigger? So suppose that I have my matching. Again, these are the edges in my matching. And I'm going to also have some other edges in my graph. Okay. If I want to have a vertex cover, for every edge of this matching, I have to take at least one of its two endpoints, right? So no matter how I choose my vertex cover, since it has to cover every edge, it has to either contain this vertex or this vertex, okay? So any vertex cover is going to contain at least one of these two. It's going to contain at least one of these two, maybe both of them, but at least one of them, right? And then maybe this vertex cover, again, contains both of them. Maybe it also contains some vertices outside. But what I know is that for every edge of my matching, my vertex cover has to take one of the two endpoints. So the size of the vertex cover has to be at least the size of the matching, right? Because remember, when I'm talking about the size of the matching, I'm counting the edges, and here I'm counting the vertices. So I always have that the size of my vertex cover is greater than or equal to the size of my matching. And this holds for every matching and every vertex cover. Okay. So it also holds for a minimum vertex cover and a maximum matching. Right. So this is the theorem that we just proved. Theorem is that in every graph G, now I'm going to write it like this, but you know what I mean. Minimum vertex cover is greater than or equal to maximum matching. I mean the size, of course. Okay. Great. But will they be actually equal? So let's just do some examples and let's see what we can get. So suppose that, for example, I look at this cycle. What is the size of the minimum vertex cover? How many vertices do I need to cover all the edges here? 2. What about the maximum matching? That's also 2. So actually, I can say this is my maximum matching. I mean, I have many choices, but let's say this one, and this is my minimum vertex cover. So in this case, minimum vertex cover is equal to maximum matching. Can we find a case where they're not equal? Well, let's just take a cycle with 5 vertices. 1, 2, 3, 4, 5. Okay. What is the size of the maximum matching here? Look, if I want to take 3 edges, I will have to take 2 edges that are next to each other, and that would no longer be a matching. So I can take at most 2 edges in my matching. This is a maximum matching. What about my minimum vertex cover? If I want to cover all the edges using vertices, what is the minimum number of vertices that I need to take? Well, in this case, it's actually 3, right? So I can take this one, it covers these 2. And then I'll have to take this one, and let's say either this one or that. So here we're saying that the minimum vertex cover is actually bigger than the maximum matching. They're not. But of course, there is a reason I was showing you these examples. The first example is an even cycle. The second example is an odd cycle. So you can probably guess what the next theorem is going to be. I'm going to say if I don't have any odd cycles, which means if my graph is bipartite, then these two are equal. Minimum vertex cover is equal to maximum matching. So this is the theorem of Koenig. It says in every bipartite graph G, minimum vertex cover is equal to maximum matching. We know one thing for sure. We've already proven that in every graph, the size of every vertex cover, including the minimum vertex cover, is greater than or equal to the size of every matching, including the maximum matching. So I definitely know that minimum vertex cover is greater than or equal to max matching. I want to show the other side. I want to show that min vertex cover is less than or equal to max matching. So we know that the size of our minimum vertex cover is greater than or equal to the size of our maximum matching. We want to prove that it's also less than. Okay. How can I do this? Basically, what I want to do is I want to find a matching and a vertex cover of the same size. Because if I find that, then the matching is definitely a maximum matching and the vertex cover is definitely a minimum vertex cover. Okay. So what do you suggest we do? Do you suggest that I start with a maximum matching and try to create a minimum vertex cover of the same size? Or that I start with a minimum vertex cover and try to create a maximum matching of the same size? Well, it turns out here you can do either, and actually both of them are quite easy. I'm going to do the minimum vertex cover thing. So let's take a minimum vertex cover of our graph, and let's find a matching that has the same size as this vertex cover. Okay. So I'm going to say let's A be a minimum vertex cover. Okay. Now, as usual, my graph is bipartite, so I'm going to consider two sides, x and y. I have some vertices here, in X. I have some vertices here in Y. And then I have my set A, which is a minimum vertex cover. So every vertex in X is either in A or not in A, right? So let me just show the vertices in A in red. So let's say these vertices in X are in A. Okay. And let's say these vertices in Y are also in A. Okay, so this is A intersect Y. This is A intersect X. And of course, these are the remaining vertices. So this is X minus A. This is Y minus A. Okay. So first of all, I know that my graph is bipartite. So every edge is going from left to right. I don't have any edges that are completely on the left. I don't have any edges that are completely on the right. But I want to see where these edges can go between these sets that I defined here. So first of all, can I have an edge like this? No, because see, A was supposed to be a vertex cover. So A should have at least one of the endpoints of every edge. So I cannot have an edge like this because both of the endpoints are outside of A. So all of my edges are either like this, so they have their A endpoint on the right, or they're like this, so they have their A endpoint on the left. Or I can also have edges that are covered by both sides. So I can have something like this. I can have this kind of edge. Right. But I cannot have an edge between the two blue parts. Great. Now I want to find the matching. How do I find the matching here? I want to basically say, let's find the matching that matches all the vertices in A. So I want to match all of my red vertices. And I want to match them to blue vertices. So here's what I'm going to do. I'm just going to say, let's cut this graph from here. Okay. I'm going to cut my graph into two parts, which is the reason why I put the red ones here down here and the red ones here up there. But I'm basically cutting the graph into two parts. Let's give these two parts a name. Let's call this one H1 and let's call this one H2. Okay. So when I do this, I will lose some edges. I'm losing, for example, this edge, right? But I don't care because I want to find a matching. I want to find a large matching. And if I have a graph and I lose some edges, that can only decrease the size of the maximum matching, right? So if in these subgraphs I can find big enough matchings, then I can find the matching in the original graphs. So here's what I claim. I claim that in H1, there is a matching that covers all of the red vertices, that matches all of the red vertices. And also in H2, there's a matching that matches all of the red vertices. Now, why is that the case? So I have to check the conditions of Hall. I have to check that every subset of red vertices has at least as many neighbors as its size. Okay, so let's look at a subset of red vertices here. How many neighbors does it have? So again, I'm only looking at the graph down here. I'm only looking at H2. And I'm not looking at all of the red vertices. I'm looking at some subset of them. So I'm saying, suppose S is a subset of A intersect X. The question is, how many neighbors does S have in this graph H2? Okay. can I claim? If I have a vertex in S that doesn't really add any new neighbors. So if I have a vertex in S such that the neighbors of S is the same, whether or not I include this vertex, right? Then I can just remove that vertex from my minimum vertex cover. So in some sense, we have this intuition that no vertex in this set S, or generally no vertex in the red part here, is added for no reason. There's no vertex that I can just remove because this was supposed to be a minimum vertex cover. Now, but I'm going to say this in a different way. I'm going to say, okay, I have the set S and I have the neighbors of S. And again, maybe this example is too small. So let's imagine that this is like a bigger thing. And let's say that I have taken some set S and I'm looking at all of its neighbors here. Okay, so these are all neighbors of S in this graph H2. Okay. Now, what is the role of S in my vertex cover? The role of S is to cover all of these edges that are going between S and its neighbors, right? Those are the only edges that are covered by this S. So if the number of neighbors, if the set of neighbors is smaller than the set S itself, what can I do? I can remove S from my vertex cover and I can add the neighbors to the vertex cover because these neighbors, they also cover the same edges. Maybe they also cover some extra edges, I don't know. But at the very least, they cover everything that S covered. Okay, so this is what I can say. I can say that the size of the neighbors of S in this graph H2, so I write it as N2 of S, is at least the size of S. Because otherwise, to prove this, I just say, suppose for contradiction, that the neighbors of S has a smaller size than S itself. I just create a different vertex cover. I say consider this vertex cover, A prime, which is the same vertex cover A that I had before, but I remove S and I add these neighbors. This is also a vertex cover. Again, the reason is that S was only covering these edges. Just go back to the original graph for a second. So what is S covering in the original graph? S is covering these edges that are going from S to its neighbors here. Maybe I also have an edge like this, but that edge is already covered by a vertex here on the right side, right? So if I remove the vertices in S, the only edges that are not covered anymore are the edges between S and its neighbors down here. But when I add these neighbors down here, those edges will also be covered. So if the size of this set, this is N2 of S, if the size of this set is smaller than the size of S itself, I can get a smaller vertex cover in my original graph. So this tells me that in this subgraph in H2, the number of neighbors of S is greater than or equal to the size of S. And of course, I can say the same thing about H1. It's just like a mirror image, right? Okay, great. So what does this mean? This means that we have the conditions of Hall in H1 and in H2. In H1, I have the conditions of Hall for the red vertices, which means that I have a matching only in H1 that matches everything that was on the red side, right? And then the same thing in H2. I have a matching only using the edges of H2 that matches everything in the red side here. So if I just take the union of these two matchings, put the two matchings together, I will get a matching in my original graph that is matching all of the red vertices, and it's never matching a red vertex with another red vertex, right? Because I cut it like this. So I have a matching whose size is the same as the size of my minimum vertex cover A. So because I created a matching whose size is the same as the size of the vertex cover, that has to be a maximum matching. This one is a minimum vertex cover. Basically, we proved this. So in every bipartite graph, the size of the minimum vertex cover is equal to the size of the maximum matching. But if our graph is not bipartite, we don't necessarily have this because we have this example. Okay. But now let's look at some other relationships between these things. So another thing that I defined in the problem set is an independent set. So an independent set is just a set I of vertices such that there is no edge that has both of its endpoints in I, such that no edge has both endpoints in I. So the idea here is that if I remove all the other vertices, if I only keep the vertices in I, there will be no edge connecting two of them. Okay. What is the connection between a vertex cover and an independent set? So this is the next theorem that I want to prove. I want to say A is a vertex cover if and only if, when I look at its complement, V minus A, that's an independent set. Why? Just follow the definitions. So what does it mean for A to be a vertex cover? It means that I have this set A. It's a set of vertices. And every edge has at least one of its endpoints in A. So I can have edges that start in A and go out. I can have edges that have both of their endpoints in A. But if you look at the vertices that are outside of A, there is no edge between them. Because if I have an edge here, then A is no longer a vertex cover. Okay. So if I have a vertex cover, its complement is of course an independence. But I can just reverse the same argument. Suppose that I have an independent set. So let's say that I start from here. I say this set, let's call it B, is an independent set. If B is an independent set, there is no edge that is completely inside B. So every edge either has both of its endpoints outside of B, or it has at least one of the two endpoints outside of B. So if I take all the vertices that are outside of B, they're going to cover all the edges, right? So this is V minus B. So if B is an independent set, V minus B is going to be a vertex cover. Great. So what does this tell you about the minimum vertex cover and the maximum independent set? Again, when we're talking about any of these definitions, we want to see what is the largest possible and what is the smallest possible. And in case of an independent set, it's very easy to find a small independent set, right? The empty set. That's a small independent set. It's quite hard to find a large independent set. So we want to talk about the maximum possible size for an independent set. But, well, I know that if I have an independent set, its complement is a vertex cover, right? And vice versa. So if I want to find my maximum independent set, I can just find my minimum vertex cover and take its complement, right? And then we have this theorem, which is basically in any graph with n vertices, size of the maximum independent set plus the size of the minimum vertex cover is equal to the number of vertices. because my maximum independent set and minimum vertex cover are basically complements of each other. And again, so the sizes, I'm talking about the sizes. When I write max IS, I mean the maximum size of an independent set. I might have many independent sets of this maximum size. Okay, so I'm not claiming that I have a unique maximum independent set. I'm just saying that the size of a maximum independent set plus the size of a minimum vertex cover is always going to be equal. And it's just because of this. Okay. We're going to define something else. So right up until this point, we've seen vertex cover. And the idea in a vertex cover was that I want to pick a bunch of vertices that cover all of the edges, right? But I can do the opposite of this. I can say I want to pick a bunch of edges that cover all the vertices, okay? And that would be an edge cover. So an edge cover is just going to be a subset. I don't know what to call it. Let's call it L, subset of edges, such that every vertex is incident to one edge, to at least one edge. Okay, so this is kind of the opposite idea than the one that we had for vertex cover. So I want to pick some edges that cover all of the vertices. First of all, a very trivial question. Does every graph have an edge cover? No. No, you don't need it to be connected. If you have a vertex of degree 0, right? If you have an isolated vertex, if you have a vertex that doesn't have any edges coming to it, you cannot cover this vertex with edges. Okay. So whenever we're talking about edge covers, we only talk about graphs in which we don't have isolated vertices. That's a stupid corner case that we have to be careful. Okay. Now, again, when we're talking about edge covers, suppose that edge covers exist. So I don't have vertices of degree 0. Is it easy to find a large edge cover, or is it easy to find a small edge cover? It's easy to find a large edge cover. Just take all the edges. If the degree of every vertex is at least 1, and if you take all the edges, that's an edge cover. So again, the interesting question is, what can we say about minimum edge cover, right? So up until now, we've talked about independent sets, matching, vertex cover, and edge cover. For independent sets and matchings, we were looking for maximum. And for vertex covers and edge covers, we were looking for minimum. Right. So can you guess something which is kind of similar to the results that we've had so far? So what are the results we've had so far about all of these 4? So we've had this one. So far, we know this. We know that maximum independent set plus minimum vertex cover is n. And this is for all graphs. Okay. But we also had this theorem of Koenig, which says that in bipartite graphs, minimum vertex cover is equal to maximum matching. So minimum vertex cover is equal to maximum matching. But this is only in bipartite graphs. Okay. But now I've defined a new thing, edge cover, and I want to see if I can find similar theorems. So here's the next theorem that I want to prove. I want to prove that maximum matching plus minimum edge cover is also equal to. And this is, let me see who proved this. I think it was Galai. Yes, it's Galai, 1959. So this is the next theorem that we want to prove. I want to say, now, importantly, I can say this only if I can talk about edge covers. So if I have a graph with no isolated vertices, so I have no vertices of degree 0. Okay. So the theorem, and this is the theorem of Galai, is that in every graph G with no isolated vertices, we have this, the size of the maximum matching plus the size of the minimum edge cover is equal to n. Now, I just want you to realize that this is a very weird equality. Because when I'm talking about a matching, I'm talking about a set of edges. And when I'm talking about an edge cover, I'm also talking about a set of edges. But I'm saying that the sum of these two is the number of vertices. Okay. Great. So let's go back to the ideas that we had from the previous theorems, and let's see how we can try to prove this. So we had a similar theorem here, right? The idea was that maximum independent set plus minimum vertex cover is n. But how did I prove this? I said basically, if I have any independent set of some size, if I have an independent set of size k, I create a vertex cover of size n minus k. Right? This is basically what I was doing here. And I was also saying that if I have a vertex cover of size k, I create an independent set of size n minus k. So if I prove those two things, then I have this. Okay. And here I want to do exactly the same thing. I want to say, suppose I have a matching. Let me go and try to find an edge cover whose size is n minus the size of the matching. Okay. And then let's start from the other side. Suppose that I have an edge cover, and let's find the matching whose size is n minus the size of the edge cover. Okay, this gives some sort of a one-to-one correspondence, not exactly one-to-one, but a correspondence between matchings and edge covers. And then it proves that if I take the largest matching, of course, I should have the smallest edge cover on the other side. Okay, so this is my part one. I want to say, if we have a matching M, of size k, then there is an edge cover of size n minus k. Now, this might look hard, but it's actually one of the easiest theorems we have so far. So I have a matching, and let's say it's of size k. So I have k edges in my matching. This is my matching. Okay. There are k edges. I want to create an edge cover, which means that I want to choose some edges that cover all of my vertices. Okay. So not all of my vertices are necessarily in this matching. Maybe it's not a perfect matching. Maybe I have some vertices that are outside the matching. Okay. But I know that I don't have isolated vertices. I know that every vertex has degree at least 1. So all of these vertices have at least one edge going out. Okay, I want to choose some edges that cover all of my vertices. I take all the edges of my matching And for every vertex that is outside of my matching, I just take one of the edges that are going out of it. Right? I just wanted to cover all the vertices. I covered all the vertices. Okay. How many edges did I use to cover all the vertices? Well, for every edge in the matching, it's covering 2 vertices. Every edge that I took from the matching. Every edge that I took from outside of the matching is covering only 1 vertex. And overall, I'm covering n vertices. So I have n minus k edges covering. Now, it might be that 2 of the edges that I took outside here were actually the same, right? So it might be that I had something like this edge was the same as that edge, right? So it might be that my edge cover doesn't actually have n minus k edges. Maybe I have less than n minus k edges, right? But what this is proving is that I'm creating an edge cover of size at most n minus k. I'm definitely not taking more than n minus k. Okay. But what if I have less than n minus k edges? Well, just add some random edges, right? It's an edge cover. It's already covering everything. I can keep adding some other edges, right? Already everything is covered, so it's fine. I can just make the size of my edge cover larger. So you can add more. Okay, but anyway, let's just put the at most there because we don't want to make it suboptimal. We say that if we have a matching M of size k, then there is an edge cover whose size is at most n minus k. Okay. Part 2. Let's do the opposites. Let's say that I have an edge cover of size k. If we have an edge cover L of size k, then we have a matching of size n minus k. Okay. This one is a bit more interesting. It says I have this edge cover and I want to find the matching. And again, just like before, here I had at most, here I will have at least, right? Because I want to find the matching of size n minus k. It's fine if I find a larger matching, because if I find a larger matching, I can just kick out some of the edges and then I'll get a smaller matching, right? So I say of size at least n minus k. Okay. So here I'm going to work a little bit on my edge cover. I'm going to say, well, maybe my edge cover has the problem that we saw here. And the problem here was that I was creating this edge cover, and then I was just adding some random edges that I didn't really need. So what I want to do here is that I want to make my edge cover minimal. Again, not minimum, but minimal. So an edge cover is minimal if you cannot remove any of the edges in it and it remains an edge cover. So basically, if it doesn't have any stupid edges that don't need to be there, if you cannot delete anything from it, right? So here's the thing. Let's define a stupid edge. Let's say that I have an edge. So suppose E is in L. So the edge E is in my edge cover. So this is the edge E. Well, what is this edge covering? It's covering the 2 vertices on its 2 endpoints. Okay, so I have, let's say, U here and V here. I say that E only covers its two endpoints. Now, suppose that both of these endpoints are already covered by something else. So suppose that this E was in my edge cover, but there is another edge here which is also in my edge cover, and there's another edge here which is also in my edge cover. So in this case, I don't need E, because E is covering things that were already covered by the other edges. I can just remove it. In this case, I say E is a stupid edge. Okay. So E is stupid if both U and V are covered by L minus E. Okay. So the first thing I do is that I keep removing stupid edges. And there is no unique way of doing this. Again, based on the order that I'm removing, different edges might be stupid or not. But anyway, I start with my edge cover L. I say as long as there is a stupid edge, find the stupid edge and remove it. So I end up with an edge cover which is minimal. It's an edge cover that doesn't have any stupid edges. Now, what can I say about that edge cover? So I'm saying suppose L is a minimal edge cover. With K edges. If I only look at the graph that has the edges in L, how does that graph look like? So try to do an example like a piece of paper, or I guess on iPads. How would this graph look like? So let me just do an example here. I have this original graph. And then I choose some edge cover. So let's say I choose these edges and these edges. Let's say I choose these edges, the red ones. Okay. Now I have to first remove some stupid edges. So this edge is stupid because both of the endpoints are already covered by something else. So I remove this edge. Okay. Now, if you look at this edge, or actually, let me see. I can also remove like this edge. Both of its endpoints are already covered. So I remove this one. Okay. And then do I have any other edge where both endpoints are covered? Well, I have this edge. Right, both endpoints are already covered. This one is covered by this. This one is covered by this. So I remove this edge. And finally, I have this edge, which is stupid. I can remove this too. I had already removed that one. And this one was not in my edge cover at all. It's like a matching. Right? But it's not always going to be a matching. So what can I say when I'm removing these stupid edges? What can I say about the degree of every vertex in the remaining graph? So if I only look at the graph that has the edges in L, so let me call that something. Let's call it the graph H, which has the same set of vertices as my original graph, but the edges are only the edges in L, which is a minimal edge cover. What is the degree of each vertex? I can have vertices of high degree here, right? So, for example, I can have something like this. You look at this graph, none of the edges are suited. But here's what I want to claim. I want to claim that if I look at each one of the connected components of this graph, the connected component is a star. And a star is basically a tree which has like one vertex connected to every other vertex directly. This is called a star. So this is a star with like 4 outgoing vertices. This is a star with 5, 6, 7. This is a star. Okay. So I would claim that every connected component of this graph, every connected component of the graph that only has L as its edges is a star. Now, why is that the case? Suppose that I have a path of length 3. So suppose that I have something like this. Then the middle edge would be suited. Right. So whenever I have a path that is longer than 2 edges, I can remove the middle edge. Okay. So in this graph that I get when I only have this L, like the minimal edge cover L, the length of every path is at most 2. So I cannot have a cycle. The length of every path is at most 2. Right. So my graph is a forest. But now I want to talk about every connected component. So every connected component of a forest is a tree. But again, I have a tree, but the length of every path is at most 2. That's basically saying that I have a star. Okay, you can check that. It's basically the same thing. So every connected component would be a star. So if I look at this graph H, how does it look like? This is how H looks like. H is a collection of stars. So it's something like this. Maybe I have a star with only 2 vertices. I have maybe a star like this. Maybe I have a star with many vertices. I cannot have just one vertex, remember, because my edges covered all of the vertices. So this is what I have. Okay. Now, the question is, how many stars do I have? I know how many edges I have, right? So the number of edges was K, the size of this edge cover, okay? So I have K edges. And I know that I also have N vertices. How many connected components do I have? Someone please tell me, how many connected components do I have? N minus K, right? N minus K connected components. I mean, I don't even need the fact that my connected components are stars at this point. I just need the fact that my entire graph is a forest. So every connected component is a tree. I don't have cycles. So if I have this connected component and if it has I vertices, then it has I minus 1 edges, right? So if I have K edges overall, I should have N minus K connected components. Okay, but where am I? Like, where did I start from? What did I want to prove? I wanted to prove that if I have an edge cover of size K, then I have a matching of size N minus K. But now I have this graph, and it's a subgraph of my original graph, right? Because it's just taking the edges in L and removing all the other edges. And it has N minus K connected components. So I can just take one edge from every connected component, right? And I don't care which edge you take. Just take one edge from every connected component. that's going to give you a matching of size n minus 2. Right. Now, again, we have this at least here because this was not my original edge cover. I removed some stupid edges, so maybe the size of the edge cover went down, which will make the size of the matching go up. Okay. So putting both of these things together, we have Galois theorem, which says that in every graph that doesn't have isolated vertices, maximum matching plus minimum edge cover is equal to n. Okay. Great. What else can we get? So look, in bipartite graphs, I know that minimum vertex cover is equal to maximum matching. In graphs that have no isolated vertices, I know that maximum matching plus minimum edge cover is equal to n. And in all graphs, I know that maximum independent set plus minimum vertex cover is equal to n. So here's what I claim. I claim that maximum independent set plus minimum, maximum independent set is equal to minimum edge cover in some graphs. What graphs should I put here? Bipartite with no isolated vertices. Why? Look, the sum of these two things is equal to the sum of these two things. So maximum independent set plus minimum vertex cover is n, and maximum matching plus minimum edge cover is also n, right? And then this one, minimum vertex cover, is equal to this one, maximum matching. So this one, maximum independent set, should be equal to this one, minimum edge cover.